Okay, so let's look at another example. So we are trying to find the limit of this sequence. We are trying to find the limit of this sequence. So when you look at this sequence, you realize it's not like the first one that we solved, okay? Because this sequence is not really having powers that you can easily divide through or something like that. So what do we do in this type of situations? Now, one thing you are supposed to know is that when it comes to sequence, you have to know how to rewrite things, because no one is going to tell you that you have to rewrite something in a nicer way. Yes, so sometimes anytime you get a sequence, ask yourself, is there a possible way you can rewrite it to make it more vivid and clear? If that's true, then you easily what do that to make the solving easier. So we have a question like this, and we are trying to find the limit of this sequence. First of all, you can try to rewrite this into a different form. Now you know that anytime you have a square root, automatically you can change it. So we are going to get, let's say, our 2 1 plus 3n all raised to the power 1 exponent n. Are we getting it? All raised to the power 1 exponent n. So now you realize that this type of sequence is a little bit what cleaner than the first one. And we also know that when you have something like this, so remember when you have a exponent 2 multiplying 3, what do? You maintain your base and you multiply the exponent. So you are going to get 2 times 3, which is going to be equal to what? 6. Yes. So the same thing is going to happen over here. Now, you can easily what? Multiply through by the exponent. So 1 times, so you are going to get 2. 1 times this is going to give you 1 over n plus 3n times this one is going to give you what? 3, because 3n multiplying 1 over n, this n is also going to cancel this n, so eventually we are going to get 3. So now this is the simplified version of the expression. So realize we've not even started finding the limit yet. All we were just doing was to rewrite this one in a nice way. Now let us find the limit. So the limit as n approaches infinity of 2 1 over n plus 3. Now, how do we go about this? Now, you remember when we were talking about the laws, right? We said if you have the limit as n approaches infinity of, let's say, a sequence and a power, what do? Find the limit of the inside and now add the what? The power. Very good. So you realize that when you come to this type of what question, the exponent itself is a what? It's a function on its own. Are you getting it? The exponent itself is a function on its own. And this one is also a constant. This one is also a constant. Remember, when you also have a constant, so let's say you have a constant and a sequence, what do? You bring the constant out and you leave the sequence inside. So we can easily what? Do that over here by bringing the 2 outside. And we now apply the limit to the exponent. So we are going to get the limit as n approaches infinity of what? 1 over n plus 3. Yes, so we are going to find this limit. Very, very, very simple. So how do you find the limit? Now you know that over here we can easily what? Plug in infinity. And when infinity is being plugged, 1 over n is obviously going to give us 0. So we know that automatically we are going to get what? 2 multiplying the limit of this exponent, which is going to give us what? Our 3. Are you getting it? So obviously we are just going to get 2 exponents what? 3, which is easily going to give us 8, which means our L exists at 8, which means this one is converging as well. So you can see that what? The sequence is converging at 8. Very, 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 very what? Simple. Okay, so let's look at the next example. So we are going to find the limit of this sequence. So when you look at this sequence, you try to understand which type of method would be suitable for this sequence. Now, when you look at this, you realize that you have some ends inside and it's a little bit clear. So you can decide to use the algebraic simplification method, or you can also decide to use the L'Hopital's method, in which I will do all and we'll see how it is done. Yes, so how do we use the algebraic simplification method? All you just have to do is to divide each term by the highest denominator of n. So when you look over here, you have n all over square root of 10 plus n. Now the denominator of n over here is what? Is n. But because it's under a square root, the highest power of n is going to be square root of n. If like the square root wasn't there, then the highest power is just going to be only n. But because there is a square root, it means the n is having another additional sign. So it means this n is not going to be just n, rather it's just going to be the square root of what? Of n. So we have our limit. Very good. So what do we do? Now remember that we always divide through by the highest power of n. And as I said, we would have used n, but because of the square root, so it means this time the highest power of n is going to be square root of n, or n exponent half. If it was to be the cube root, the same thing, cube root of n. Any type of root you have, the highest power of n is going to be that with the same root. So we are going to get, yes, very simple. We are going to get what? N divided by the square root of n all over the denominator also divided by the highest power of n. Now we can continue simplifying, because we know that anytime you look at the numerator aspect, now you can rewrite this one as what? As n over n exponent half. Are you getting it? And you know that with indices, anytime you have the same basis, what do you have? You subtract. So eventually 1 minus half is going to give us what? Is going to give us half. So on top, we are going to get the square root of n all over. Now, when you look at the denominator aspect too, now you know that anytime you have what, let's say square root of a over square root of b, you can easily what? Say that you have a over b. So the same thing is going to happen over here. We put everything under the same square root. We have 10 plus n all over n. Now we can easily what? Solve this one simple by finding the limit inside the what? The square root. So you know that over here, so let me just continue over here. So we are going to get what? The limit as n approaches infinity, square root of n all over. Now this place, remember we are going to divide everything by the highest power of n. So we are going to get 10 divided by n plus n divided by n all over n also divided by n. Yes, so the square root is actually covering everything. So what do you think we are going to get? We are going to get the limit as n approaches infinity. We are going to get square root of n all over. Now 10, 0, we are going to get what? 0 plus 1 all over 1. So eventually we are just going to get the limit as n approaches infinity of n all over square root of 1. Now with this, you can easily substitute your infinity inside, and automatically we are just going to get what? Infinity, which means this sequence diverges. Yes, this sequence diverges, because you realize that when you input infinity into this one, and since this one is just alone, when you input infinity over here, it's just going to go to infinity, and square root of 1 is the same thing as what? 1. So our sequence over here is going to diverge. Let's look at how we are going to use a L'Hopital's rule to solve the same problem. Now, a L'Hopital's rule, what does it say? Or when do we know we can use L'Hopital's rule? Now, when you input infinity into this expression, you realize that what? N is going to go to infinity, and the denominator is also going to infinity. So we have an indeterminate form. Now, anytime you have an indeterminate form, automatically the best rule or method to use is the L'Hopital's method. Now, how do we go about this? Now, before you can even use the L'Hopital's method, Once you realize you can use it, the first thing you are supposed to do is to represent the sequence as a function. You have to represent the sequence as a function. So you say, let f of x be equal to, now wherever you see n, you replace it with x. So we have 10 plus x. Very simple. And with L'Hopital 2, what do? We differentiate the numerator and we differentiate the denominator. Then we simplify. After simplifying, you insert your infinity into the expression and check whether when you simplify you are going to still get an indeterminate form or is going to what simplify. Yes, so you make sure that you differentiate until you don't get an indeterminate form again. So let's look at how we are going to do it. So our limit as x approaches infinity, so we have what, our x all over root 10 plus x. So what do? Remember, we differentiate the numerator, right? So when you differentiate the numerator, what are you going to get? You are going to get 1. And when you differentiate the denominator, now remember we have is the same thing as 10x or half. And with differentiation, what do? All you do is what? Anytime you have something like this, you apply the chain rule. So first of all, you differentiate this. You are going to get 10x multiplying with 1. Yes. And remember, we forgot to add this half over here too as well. So we are going to get our half over here, because anytime we differentiate, when you multiply the expression by the exponent, you subtract 1 from it. So you realize that anytime you subtract 1 from half, you are going to get negative half. Yes. So we are going to get negative half over here. Now then you try to see if you can what, simplify. So after differentiating, what do? You simplify. So the first method is you differentiate. After that, you what, you simplify. It's very very important, because someone can also say, okay, let me just put x is equal to infinity over here, and obviously everything over here is going to go to infinity, then I'll get 0. Now that is going to be wrong. So what you do is, after you what, you differentiate, so you've differentiated, then what do? You try to simplify. So how do you simplify this? You have 1. Now this is to the power negative exponent, so just drop it down. You are going to get 10 plus x, or exponent what, half. Now you can continue simplifying. Now you know that anytime you have a fraction like this, you can easily reciprocate, isn't it? So you can get something like 1 times 2 10 plus x all raised to the power half all over 1. Yes, and you can easily write this as what? So you have your limits as x approaches infinity of, so let's rewrite this as 2 square root of 10 plus x. Now I realize now this one has become a simple simplification that we've done, and we can easily get our limit over here. Now wherever x is infinity, what do you think is going to happen? Obviously this sequence is going to go to infinity as well, which means this sequence is diverging, it's not converging. Now realize, if you didn't simplify and your you just inserted your x over here, what do you think is going to happen? You will think you are going to get 0 over here. And when you get 0 over here, you realize 1 over 0, you are going to get what? An undefined, or yes, you are going to get an undefined what, function, which is not going to work. Because if, like you said, 1, and when you put in infinity over here, you are going to get what? 0. Now you can't divide by 0, which means this is not going to work. So you have to simplify and get your final answer. Okay, so let's look at another example. Let's look at how to find the limit of this sequence. Yes, so remember we have methods of finding the limit of the sequence. So you look at the question and try to see which one is going to be suitable. Yes, so with this type of sequence, you realize that we can't divide by the highest power of the denominator, because there is no fraction over here, which means obviously we would have to use a L'Hopital's rule. And how do you even confirm that? Now, before that, you can even rewrite this one as what? As n exponent 1 over n. Because you know that anytime you have a square root, you can easily change it. If it is a square root, here becomes 2. If it's a cube root, here becomes 3, so on and so forth. So we know that this is now going to be our what? Our sequence. So our an is going to be n exponent 1 over n. Now, we know we are coming to use the L'Hopital's rule. So using the L'Hopital's rule. Now, what's the first thing we are to do when we are to use the L'Hopital's rule? And you also know that over here, when you insert infinity over here, you are going to get infinity over 0. And you know that this one is an indeterminate form. So obviously, we are still going to use the what? The L'Hopital's rule as well. So we would have to change this one into a fraction to be able to what? To solve. And L'Hopital's rule is going to help us. So for L'Hopital's rule, the first thing is to represent the function or represent the sequence as a function. So you say let f of x be equal to x all over x exponent 1 over x, because with L'Hopital's rule you can't maintain the n. You would always have to change the sequence into a function. Very good. So after you've represented it this way, what is the next thing you do? Now you know that you have f of x which is equal to x all over 1 over x. We are trying to simplify this to find x. And there is no possible way we can easily simplify this, but rather we can use the natural log to easily bring this exponent what downwards, because this is the form right now. When you input infinity, you are having infinity over 0, and this is an indeterminate form. So because this is an indeterminate form, we have to change it into a fractional form. So how do we change this into a fractional form? By removing this exponent from there to change it into a fractional form. So to be able to remove this exponent, what do? We introduce a natural log. So you take the natural log of the function and also take the natural log of the right hand side. Now when you do this, what's going to happen? You realize that you are going to get 1 over x natural log of what? Of x. And obviously, we are also going to get natural log of x all over x. Very simple. So you realize that we have changed this indeterminate form into something like this, because when you put theta m, when you put infinity into this, what are we going to get? We are going to get infinity. When you also put n is equal to infinity or x is equal to infinity over here, we are also going to get what? Infinity. So which means we are now having a fractional form which would be easier for us to solve. Now what do we do next? Now you know that with L'Hopital's rule, we have to differentiate the numerator and the denominator. So you have ln x all over x. When you differentiate ln x, now you know that anytime you have ln x, if you differentiate it, you are going to get 1 over x. So automatically we are going to get 1 over x all over. Now when you differentiate a variable, you are also going to get a constant. Yes, so this is what we are going to get. So eventually we are going to get 1 over x. So what do you do next? You try and find the limit. So you try and find the limit as x approaches infinity of 1 is to x, which is going to give us what? 0. Because you know that 1 over any variable, as long as that variable is going to infinity, your output is going to give you what? 0. So you know that over here the limit of 1 over x is going to give us what? 0. But remember that we are still not done. Because you have ln of the function which is equal to 0. Now you are trying to find this function. We are not trying to find the ln of this function. Some students forget and always leave their answer as 0, which might result in a very big problem. So all you have to do is, because we are looking for only f of x. Now if you have the ln of something and you want to cancel out this ln, what do? You raise it to the power e. So you raise this one to the power e, so you have ln of f of x, and you do the same thing also to the what? To the right hand side. So eventually this e is going to cancel this length. So we are going to get f of x is equal to e exponent 0, and e exponent 0 is equal to 1, which means this one converges at a value of 1.